Um, Welcome back to analysis. So I just want to continue going through more of the problems of chapter 5. There are quite a bit that I didn't get to, and then work our way through the chapter 6 on continuous functions. There are considerably fewer problems in that chapter, so with any luck, should be able to complete it. I mean, I'm kind of skipping over a bunch because it's not really very profitable to do all of them. But there's only 17 in chapter 6, so yeah, realistically should be able to do a good chunk. And then there are only 2 more chapters before we get to derivatives. There's the chapter 7 on 3 hard theorems, and then chapter 8 on least upper bounds. This is kind of where the real number system will be kind of completely defined. Up to now, we aren't, strictly speaking, like working with the real numbers because we haven't laid out the most important property of them, which is the least upper bound property. That's what we'll get to in chapter 8. But for now, yeah, I'll just continue with these problems. So the last one I did was number 8. I'll now do number 9. So this one says prove that the limit f of x as x approaches a is equal to the limit of f of a plus h as h approaches 0. This is almost so obvious as to like not even deserve mention. Actually, the phrasing of this is kind of weird because I mean, it's assuming implicitly that the limits exist. So the way you should actually say it is it's not like this, but if show that the limit of f of x as x approaches a exists if and only if the limit of f of a plus h as h approaches 0 exists, and in this case they are equal. All right. So I'll just do this direction, going from left to right. So let's suppose the limit of f of x as x approaches a exists. And let's suppose it equals L. Let's give it a name. So then by the definition, just using the epsilon delta definition, we can write this: for all epsilon bigger than 0, there exists a delta bigger than 0, such that the f of x minus L would be less than epsilon whenever 0 is less than x minus a less than delta. All right, and we put this 0 here just to recall that 0 is only placed there to make sure x is not actually equal to a. So this forces x not equal to a. Yeah, so we don't actually care what the function does at a. We just want to we want to know what it's doing nearby. Okay. So we've got this. Oh, I forgot to write exists up here. So we can kind of get everything like in one fell swoop here. It's just a matter of like rewriting the definition. So let me just write something similar. I'll write what it would mean for the limit of f of a plus h as h goes to 0 to exist. There is delta, not there delta. Okay. And, okay, well, this is what it means for that limit to be equal to L as h goes to 0. Once again, you put a 0 less than, just as for the other case. Alright, so yeah, these ideas or these statements are almost completely identical. Why don't I call this 1 and this 2? So you can see that 1 and 2 are completely equivalent. By setting x equals a plus h. So if you want to get from 1 to 2, you replace all the x's with a plus h, and then you see you get the absolute value of h less than delta, and you get exactly the inequality up over here. Get rid of those. And conversely, this is setting x equals a plus h. I mean, that's equivalent to setting h equals x minus a, and that gives you a way from going from the second statement, statement 2, up to statement 1. You can see that the only two parts that are different, they actually become their counterparts in the other statement when you make the substitution. Right, so yeah, not only are these limits equal, but they're even like equal for the same epsilons and deltas. Like the statement is almost identical. It's just a simple change of variable. But I mean, as obvious as it is, to rigorously show it, it's just a matter of writing out the definition, and then you can just now make the change of variable once you have the statement written out, and then it becomes obvious. Okay. I think that's sufficient. I mean, I guess I did both of these at once. I can erase that. Right, and then but sometimes so here, I mean, okay, more natural way to write this would probably be to say like that and that, just because of how the proof went. Sometimes it's easier to show one exists if and only if the other exists, and then only afterwards prove that they're equal. Yeah, I think that's enough for this problem. Okay. All right, let's see. So this will be number 10c. So prove the limit of f of x goes to 0 is equal to the limit. Oops, I was trying to write an f there. Bad muscle memory. Right, so this one's a little more interesting. It's not just a simple like linear change of variable, going from like x to x minus a, or h to x minus a, or whatever you like. So here we have the argument of the function being replaced by x cubed. And in this case, it's not going to be like, it's not just going to follow out immediately from the definitions. There is a little bit extra that we will have to do. Once again, like the way this statement should be written is that the limit of f of x exists and equals something if and only if the limit of f of x cubed exists and equals that thing. But I'm not going to fuss over that anymore. Yeah, all right. So let's suppose the limit of f of x as x approaches 0 is equal to L. Then for any epsilon bigger than 0, same drill. Here's delta. Oh, I did that again. There is delta bigger than 0, such that the f of x is within epsilon of L whenever, now just absolute value of x less than delta, and I need to put my 0 here as well. 0 less than absolute value of x less than delta. Okay, so yeah, this is okay. Let me call this left thing 1. Sorry. Right. Oh, yeah. And so what we're trying to show for any epsilon bigger than 0, there is a delta. I'll give it a tilde because it might not be the same as the first delta. Bigger than 0, such that x cubed minus L is less than epsilon whenever 0 less than absolute value of x less than delta tilde. Alright, so these do look quite similar, but they are not quite exactly the same as for like our previous problem. They were essentially exactly the same. So if I call this 1 and then this one 2, so how do we get 2 from 1? Well, you see that the only things differing in these definitions are, of course, the deltas, but, well, delta tilde is under our control. We get to choose it. So that's not a huge problem, but a bigger problem is the fact that we just have an x here, but here we have an x cubed. But in statement 1, I mean, x is just some variable. Like all we need is that this this holds whenever the thing we put inside the function f is smaller than delta. So 1 actually implies that for any epsilon, we get the same thing essentially. But now I'm actually just going to replace all the x's with x cubed. It's perfectly fine to do it, because as long as it's saying that the thing you're putting inside your function is less than delta, then the whole statement will hold. It doesn't matter what sort of expression you replace your x with, as long as all of them get replaced with the same thing. Okay. But now there's another problem. So our this modified version of 1 now has an f of x cubed, but that's come at the cost of changing a different part of it, namely this x cubed down here. So now this is the part which differs from statement 2, in which we have an x. But that's actually easy to fix, because, well, I can take the cube out of the absolute value. Just like that. And taking cube roots, the cube root function is monotonic, so it'll preserve the inequality. And so I can actually take, I can take both of these to the 1/3, where of course 0 to the 1/3 is just 0 again. So that just remains 0. But now we have absolute value of x less than delta to the 1/3. So what this tells us is that we should set the delta tilde equal to delta to the 1/3. Because that is the range within which x should be taken in order that f of x cubed be within epsilon of L. Right, so there's no reason that the delta tilde and the delta need to be the same. We just have to be able to find ones that work. And if we have a delta that works which shows the limit of f of x equals L, then this tells us how to find a delta tilde, which will show that this modified function has a limit of L as well. All right. So yeah, you can often prove things, and of course, well, yeah, you could do the same sort of thing with any power, really. Whether it's odd or even, it doesn't matter, because at this stage where we took the 1/3 power, all the numbers involved are non-negative, and it's a chain of inequalities of positive, non-negative numbers. So yeah, you're perfectly fine to take the square root of that, or whatever inverse power you like. In fact, I think this problem comes later. Oh, wait. Yeah, so if actually let's do part D. So part D, this is actually why you have to be very careful when you make these kind of statements. So where the limit of f of x as x goes to 0 does not exist. But the limit of f of x squared as x goes to 0 does exist. Yeah, so when you want to, so right, like, it turns out like if, right, let me just mention, whereas if the limit of f of x as x goes to 0 exists, then the limit of f of x squared x goes to 0, and let's say it equals L, also exists and equals L. So like if the limit of f of x on its own were to exist, were known to exist, and equal a value, then we could run our same argument up here. It would go through perfectly fine because our assumption is so strong. Okay, but if we do not know from the start that the limit of f of x itself exists, then it still could be true that the limit of f of x squared could exist. So for our example, you want to try and make things as simple as possible. So one observation is that the function f of x squared, it's an even function. So what that means, so g of x is even if g of minus x is equal to g of x for all x. Essentially, it's equal to its reflection about the y-axis. So, in other words, that also means it's determined by what it does on either side. So, yeah, it's determined by what it does on the positive x for positive values of x. So when we take f of x squared, like whatever f is doing for the negative values of x, those kind of become irrelevant when we look at this f of x squared function. So we can do something very simple, like just have a function which is a constant. Maybe I'll draw it in a different color. So we have draw the function in purple. Let's say it's got a jump there. So here's f of x. And then below, let's just draw f of x squared. Well, maybe I'll do that in green. My purple was really thick for some reason. Alright, so f of x squared for positive x, or at least for non-negative x, it's actually going to be the same constant value. And now, well, we've already determined it for the positive values, and we also know that it's even. So to get the rest of this function, since it's even, you just have to reflect what we know about it so far about the y-axis. And so this function is actually everywhere equal to a constant. You can see from the picture that the limit of f of x does not exist, whereas the limit of f of x squared, since the f of x squared is a constant, the limit for that must exist. And so, yeah, that's basically the essence of this proof. You might wonder too, like, what if, like, could we do this kind of counterexample for f of x cubed? The answer is no. That actually would be if and only if, in the sense that I described how you make these statements, like from the top here. It would look something like this. Limit of f of x exists and equals L, if and only if the limit of f of x cubed exists and equals L, both as x goes to 0. Whereas a statement like this does not actually hold for f of x squared. So here, our statement is limit of f of x approaches 0, exists, and equals L. So that implies that this exists and equals L by a similar calculation as we did in part C. But the reverse arrow does not hold because of our counterexample. So this is not true. So the limit of f of x may not even exist at all, as this shows, even if the limit of f of x squared does. If the functions are continuous, then yeah, you will be able to reverse the implication, I believe. Yes. So the only obstacle to like making this an if and only if is potentially discontinuities. When we get to chapter 6, maybe we'll talk about that. Oh, interestingly, this also shows that composing a discontinuous function with a continuous function, well, I haven't defined what those are, but like, I mean, you can intuitively see what that means, but we'll talk about it later. But composing discontinuous with a continuous can sometimes be continuous. It could also be discontinuous, but yeah. All right, that's a nice problem. And oh yeah, also if never mind, sorry. Let's see. All right, I'm going to skip ahead to 14. There's some intermediate problems on the squeeze theorem, which I'll skip over. But this one is interesting. It leads to a whole host of examples, which are kind of good to go through. Okay, so let's suppose we have this limit of f of x over x as x goes to 0 and it equals little l. And let's say b is a non-zero number. Okay, and we're now going to investigate. Alright, find the limit f of bx over x. So at first you might think, well, bx is going to 0 and x is going to 0, so nothing's changed. So it should just be little l. That's not true. Because, well, if f of x were just equal to x, for example, x over x is 1, and that approaches 1. But then bx over x is actually b, which does not necessarily approach 1, unless b is 1, but there's no point in just doing that because it's the same as the original. So the thing here is that the top is, the argument of our function is approaching 0 at a different rate than the bottom. However, we can do a little bit of manipulation to it by multiplying and dividing by b in order to make the top and the bottom resemble one another. And if you do this, the top and the bottom go to 0 at the same rate because they're the same. But it comes at the cost of introducing this factor of b out in front. So the limit of fbx over x is actually the same as the limit of b times fbx over bx. By the way, like strictly speaking, we're kind of presupposing that the limit of fbx over x even exists. So what we would do is like try to make a guess as to what it should be. But I mean, pulling this b out, we have f of bx over bx, and then we get b times, we know that's going to go to L because it's f of something over something, and that thing is going to 0. It's the same thing in the top and the bottom, so now it is valid to replace that by L. So we have b times L. Alright, so let's actually verify this using epsilon and delta. Like I said, this line of reasoning isn't really strictly speaking correct because we are assuming the limit exists. But it's not so bad. So let epsilon be bigger than 0. And okay, I don't know yet what delta will be, but I'll just leave that a blank for now. So we're going to fill this in. Alright, so now the thing which we want to make small is this. This minus b times L. And of course, okay, well, you can simplify this a bit. We get this guy. Right, and then this can be made less than epsilon over absolute value of b, provided b times x is close to 0. So how close? Well, yeah, that depends on what the epsilon and delta you need in this limit statement. All right, but okay, so assuming we've kind of looked at that and found a delta which works for this thing, right, let's say that bx is less than some delta tilde or something like that. Well, then that implies absolute value of x is less than delta tilde over b, over absolute value of b. Right. So what this says is we should take our delta equal to the delta tilde over absolute value of b, where delta tilde is a delta which comes from, which you choose for this limit, which makes f of x over x with an epsilon of L, as long as the input for that is sufficiently small. Okay. Right, so that's kind of how you would just clinch this proof, cinch this proof, I guess. All right, so now an interesting follow-up question is what if b equals 0? Okay, so to answer that, okay, let's look at f of bx over x. That's actually just going to be f of 0 over x. This is an entirely different situation because we cannot do the trick where we multiply and divide by b now, because it would be divided by 0. Moreover, the inside of the function is no longer changing. It doesn't even depend on x anymore. It's just this is just a constant now. So there's a lot that's different about this case. It's actually not so bad. So there are two possibilities, right? So the two options, either f of 0 is 0 or f of 0 is non-zero. Okay, I'll call them 1 and 2. So in case 1, well, our function actually just reduces to 0. And I mean, that approaches 0 no matter what. Even though we're dividing by an x, doesn't really matter because the 0 killed it. If it's non-zero, sorry, divide by 0, geez. If f of 0 is non-zero, then the limit x as x goes to 0 does not exist. So Yeah, so we actually get the conclusion, limit of f of 0x over x equals 0L in the first case, but in the second case, so this actually follows the template for part A. Limit of f of bx over x, that was found to be equal to BL. However, if f of 0 is non-zero, then the limit just doesn't exist. Okay. So now C, that we investigate here the limit of sine of 2x over x as x approaches 0. And now we want to assume, or we're allowed to assume this like this trigonometric limit. All right, and this is a special case of the assumption for part A. We have a limit of f of x over x equaling L as x goes to 0. So that's what this is. And now here our b is equal to 2. So we know from part A, this is a special case. So we know it's going to be b times L, so 2 times 1. That's little l. So it'll be 2. Alternatively, we can do this a different way. So we can actually we can expand the sine of 2x using a trig identity. So using this identity, and we should get the same thing. So, right, what's interesting here is like our argument was very general. It doesn't matter how complicated the function looks just by rescaling the input on the top. We can find the limit in terms of the original limit, as long as the limit existed in the first place. But depending on the form of the function, we can also sometimes use special properties that they may have in order to evaluate the limit in a different way. And we know from the theorem on the uniqueness of limits that we should get the same answer no matter how we do it. Right, the way we want to think about this one, we have a division by x, but we also have a sine of x, and we know the limit of those things divided by one another is known. That's equal to 1. So it's a 2 sine x over x together with a cosine. And as x goes to 0. So we can think of it as a product of 3 terms. The 2 sine x over x and the cosine, all of whose limits exist at 0, and therefore by the limit law for products, we can take the limit of each thing separately and multiply the results. Of course, we need to make sure those limits all exist. We can't just be like, oh, like limit of 1 over x and limit of sine x and limit of cosine x, and like that doesn't work because 1 over x doesn't have a limit. But if you combine a sine x and a 1 over x together, then it's all good. So 2 approaches 2, this approaches 1, and the cosine approaches 1, because it turns out it's continuous. We'll get to that later. And the limit's 2, which is what we expected. So yeah, you can see we have options. If you had something like a sine of 100x or something, the first way of doing it is much more preferable to this expansion method for obvious reasons. If you try to do it, if you try to expand like sine of 100x, you'll find it's going to turn into an enormous mess very quickly. But we can just do it in an instant using this general limit argument. All right, well, I kind of spoiled what the value of this is. It's equal to 1, but, you know, I'll just call it alpha now. So problem 15. So we've got a bunch of these complicated looking limits in terms of sine functions. But for the most part, we can evaluate them with several little tricks and using the result which we just proved on this rescaling of the function. So for part 1, so we want to start with sine 3x over x. Sorry. Yeah, and like I was saying, you could try expand it, but we already know that it's just going to be 3 alpha. And the trick was, well, you can just do the trick. So multiply and divide by 3. This whole thing goes to 1, or sorry, alpha. I shouldn't be saying 1, we haven't proved it. Yeah, and then we get that. We get 3 alpha. The second part, sine of ax over sine bx. Once again, it says x goes to 0. Okay, so for this, we should actually look at like a couple of cases. So I mean, assume a and b are not 0. B can't even be 0, like even in theory, because we're dividing by sine bx. But a, I mean, even if a is 0, which it is allowed to be, the whole thing just turns to 0. So there's really no point in considering having a equals 0, because it just collapses everything. So we'll assume they're both non-zero. So what we do here is actually just take the top and bottom and make these quotients appear. We can't just do that though, we need to also multiply by the things we introduced so that we don't change our expression. And okay. So now you'll notice actually that we have an x factor in the top and bottom, and that means we can cancel those off. Maybe I'll draw that in red, sorry. So we can get rid of those. And then our a over b, that can come out. And you'll notice both of these limits on the top and the bottom, they exist. So we have the limit sine ax over ax divided by the limit sine bx over bx. Both of these approach alpha. And so we're finally left with a over b. Right, because like even though we've got a sine of ax, we're also dividing by ax, so it's really sine of some quantity over itself, and that gives you the same limit as sine x over x. Right, so we're left with a over b. Alright, yeah, let's keep going. So, some more of these. If we have a limit x going to 0, sine squared 2x over x. Yeah, so don't be too tripped up by this. Intuitively, what you want to sort of think with this one, so that we have a squared factor of the sine on the top. So really roughly speaking, we've got an x which is going to 0, but that's only of order 1. And you've also got a sine of x, or sine of 2x, I guess, factor, which is heading to 0. But we have 2 of them, so we're multiplying by it. So the top is going to 0, and it's roughly order 2. So we would expect the end result to just be 0, because the top's going to 0 faster than the bottom. It's going to 0 roughly twice as fast, I guess, because of the square. Okay, so as for proving that rigorously, we first want to rewrite this expression a little bit. So this x, we can pair it up with one of these guys. Makes it look like that. And now we are now ready to take the limit. So this is going to go to 2 alpha from problem 14, part A. And then that's going to go to 0. So all told, as x approaches 0, and these are all as x goes to 0, we are going to have our original function approaching 2 alpha times 0, which will just end up being 0. Alright, so now we're going to look at the same thing, except it's going to be over x squared. So here, the top and bottom are now going to 0, both the order 2, but we can still simplify it with the same kind of approach here. These both go to 2 alpha now. Alright, so not too much has changed. It's just that we have 2 factors each going to the 2 alpha. So the result goes to 4 alpha squared. Okay. So now for this one, we can't just do this directly. Actually, okay, well, you always want to try, see if you can just plug things in, and if that doesn't work, then we have to use some other tricks. I mean, basically none of these problems are going to allow you to just plug a number in, but so we need to remember this trig identity. That's the most important trig identity. Sine squared x plus cos squared x equals 1. And the form which we want to use is this. Sine squared x equals 1 minus cos squared x. Alright, so the reason we want to do that is so we can introduce some sine x factors, because that's the expression in terms of which we want to write all these limits. And right now we have a cosine, but we can introduce a sine by leveraging this identity. So what we need, well, we have a 1 minus cosine x. So all we got to do is multiply the top and bottom by this. It's kind of like rationalizing the numerator, but with trig functions. And this will turn into 1 minus cos squared, which by the identity gives you sine squared on the top. Okay. So we get that. Right. And now all of this stuff, that's just going to approach alpha squared. And the bottom, 1 over 1 plus cosine of x, times 1. All of that, putting in the 0 for x, that's going to approach 1/2. So we get 1/2 alpha squared. Okay. Now this one involves a tan function. There's also a whole bunch of other stuff, most of which is kind of irrelevant. Yeah, so this looks like totally nasty, but you want to just look for ways to simplify it as much as you can. So first off, we can actually like split this into two terms. Splitting it like that. And the second piece, this will actually go to 0 because the bottom is quadratic, whereas the top is only linear. In fact, well, like you could divide out an x factor. There's an x common to the top and bottom. And then this obviously just goes to 0. So that term is basically irrelevant. Now let's look at this guy. So this is actually sine squared x over cos squared x divided by x plus x squared. Okay. So now we have this sine squared, which is going to 0. We also have an x squared, which is also going to 0. So it would be kind of nice to try and pair those together. So what I want to do is like rearrange this. Sine squared x over x squared. I'm going to pull out an x squared from these two. So that leaves me with a 1 over x plus 1. So that this x squared here Oh, excuse me. This x squared on the bottom, so it just comes from factoring out an x squared from the two terms in the denominator. Just put that. Right, we're left with 1 over x plus 1, and now we also get 1 over cos squared x. Okay, so now that we've written it this way, we are ready to see what the limit is. Sine squared x over x squared, well, we've already done that. That's alpha squared. 1 divided by 1 over x plus 1. This guy goes to 0, so the whole thing goes to 1. Cos squared goes to 1, so 1 over cos squared goes to 1. So, alpha squared times 1 times 1, which is alpha squared. Maybe I'll do one more. Maybe two more. Yeah, so this is part 8. That doesn't matter. Okay. Yeah. So, yeah, if you've done any calculus before, you'll recognize this as the definition of the derivative of the sine function at the value x. And we can actually figure out what this is in terms of the fundamental limit, the limit of sine x over x, which I wrote up here, which I said is equal to 1, but we haven't actually proved that yet. Okay. So, in order to evaluate this, we need this trig identity here. Didn't quite give myself enough room. Barely fit. Okay. So sine A cos B plus cos A sine B. As for how that's proved, maybe, well, we'll talk about it later, but I'm going to take it on faith for now. Right. Okay, so I'm having h as it's kind of confusing with the hyperbolic trig functions, but all right, so now we can kind of split this up in a clever way. So h goes to 0, sine of h also goes to 0. So we know we should probably stick those two together. And then what this leaves us with is this. Alright, so let's just look at what happens. Cos of x is independent of h, so that will just be left unchanged by the limit. But that's going to go to alpha. for this other term, we can start by factoring out sine of x. And we have cos h minus 1 over h. Now, if you look up, did I do that right? Oh yeah, so you can deal with that second one in a similar way to how we did the previous one of these previous problems, number 5. Where you rationalize the numerator. So if you do that, you'll actually find that this stuff actually goes to 0. So the second term will vanish. We're left with alpha times cosine x. Okay. So maybe as a challenge, I'll just write down problem 11. So problem 11 is this. Same idea you want to try and figure out this limit in terms of alpha, which is the limit of sine x over x as x goes to 0. Okay, so 16. Yeah, so if the limit of f of x equals L, and this is as x goes to A, then the limit of absolute value of f of x is equal to absolute value of L. All right. So what one says is this, for any epsilon bigger than 0, there's delta such that f of x minus L less than epsilon whenever the x minus A is less than delta, 0 less than x minus A less than delta. All right. Oh yeah, and I just want to mention too, absolute value of f of x, by definition, that just means you take f of x and take its absolute value. So it's just sort of a notational thing. I mean, we're defining a new function, which is actually like put the bars around the letter f. So that whole symbol represents the function, which means take f of x and then take its absolute value. It's really a composition. It's equal to the absolute value function, ABS, composed with f of x. But this is another way of denoting that. So it looks even if it looks kind of weird. Okay. Right, so then the 2, we want to get we want to prove the counterpart of statement 1 for the function absolute value of f of x. So the trick here is to use the triangle inequality. And we want to use the form which goes, sorry, the lower bound form. I don't even know what the technical name for it is. But it looks like this. So the triangle inequality, there's 2 versions. I mean, they're really the same, but you can either use it to get an upper bound or a lower bound for an absolute value of a sum of 2 things. And here we want to use the lower bound version. Okay, so yeah, so let epsilon be bigger than 0. Now we want to choose delta. So the absolute value of f of x minus L is less than epsilon whenever x minus a is less than delta. And now, with this choice, this difference is less than or equal to f of x minus L by triangle inequality. So triangle inequality. And this will be less than epsilon from right here. At least as long as x is close to a. So as long as x is within that delta, which was chosen of a. And we know we can choose the delta by statement 1. That's just the statement that the limit of f of x equals L. Okay, and yeah, that actually proves it, because this says exactly that absolute value of f of x is within within epsilon of absolute value of L, provided x is within delta of a. That's exactly the statement that the limit of absolute value of f of x equals absolute value of L. Okay, well, I did not make very much progress, but yeah, I think I'm going to stop there for now. Not sure how long I've been doing this. Let me see. Yeah, anyway. Well, it looks like limits will take maybe another session or 2. I was a little optimistic as to how much progress I would be able to do, get progress I'd be able to make. But that's okay. We'll just keep plodding along. I'll try and make the videos more regularly from here on out. And yeah, we'll eventually get there. All right. See you later.